day, mathletes. So 5.2, the definite integral we're working on, and this will probably be a 2 or 3 part section. But remember, we learned last time we were given an area formula where we kind of derived or arrived at an area formula, and it was this right here, right? And remember that basically what this is the length times width of a rectangle, and then we're summing up as many rectangles we can, right? Because we're going from 1 to n, where n is approaching infinity. And so we're trying to squeeze as many rectangles we can into that curve. That's helping us to approximate the area of the curve, right? Well, it turns out that the definite integral is equal to that area formula. So the definite integral, what it does is it finds the area underneath the curve. And it has all this stuff basically built into it, okay? So you can kind of see it in certain, in a sense, in pieces. You have this f of x, and here we have f of x sub I, and so that's our length, right? And then we have our delta x here. Instead of delta x, we have dx, right? And so this is kind of like length times width. And then we have our a and our b built in, okay? So we have a and b built in, which are the endpoints of our interval, okay? Or the bounds of our integral. All right, and then the integral basically does the work of this right here. Okay. All right. So if the limit exists, then the function is said to be integrable on a to b, or it's just an integrable function. All right. So continuous functions are integrable. Integrable. Excuse me. So if we have if we know a function is continuous, then it must be integrable on that interval, or in general, if the function is continuous in general, that means that it'll be integrable everywhere. All right, and so let's look at how we can evaluate this. So here it's saying evaluate using the definition, right? So we're given that definition. So remember that our definition is the limit as n approaches infinity of the sum from I equals 1 to n of this function. So in this case, it's x squared. And remember, the way we do this is f of x star sub I. And that star means it could be right hand or left hand, right? It could be upper or lower, delta x, okay? So remember that delta x is equal to a, or b minus a, right? So in this case, b is 2 and a is 0. So it's 2 minus 0 over n, right? N is something that approaches infinity, so we're just going to leave n in there as a variable. Okay, so basically there's just 2 over n. All right, so I'm going to put 2 over n here. All right, and so now let's find f of x sub I. All right, so let's think about what x sub I is. So x sub I, remember that if we have an interval, we can, and let's just draw this out here. So we have this function x squared, it looks like this, right? And in this case, we're going from 0 to 2, right? But if we just generalize x sub I, then we're going to start somewhere at x sub 0, right? So whatever, like this first term is going to be x sub 0, right? And then we'll end up at x sub n somewhere, right? And in between here, we're going to have a bunch of delta x's, because remember, delta x is the width of each rectangle, or the distance from one x to the next, right? So if I go x sub 1, that distance right there is delta x, right? And so x sub I, the next item in the list, x sub I, is going to be x sub 0, wherever you start out at, plus delta x times I, right? However many delta x you have, because if I is 1, you just go 1 delta x. If I is 2, you're going to have 2 delta x's, right? Delta x times 2. If I is 3, that means you're going to go to the third delta x. So every time you get to the next I value, you move another delta x. And so it's I times delta x, right? And so another way to write this is x sub 0 is going to be a, right? So it's a plus I delta x, all right? And so in this case, delta x is 2 over n, right? So let me rewrite this. So x sub I is going to be a, which is 0, right? So I'm going to put 0 in here for a, plus I, and then delta x is 2 over n. So it's I times 2 over n, or, to cancel out that 0, so it's just going to be 2I over n, right? So I'm going to put 2I over n here. All right, so f of 2I over n, so if I put 2I over n in for x squared, remember this is the input into that function, so in this particular case, our function is x squared, so it's going to be 2I over n squared times delta x, or dx, which is 2n, right there. And so if I simplify this, then it's going to be 4I squared over n squared times 2 over n. And so that'll end up being 8I squared over, and I forgot to square the n down here, over n cubed, right? N squared times n is n cubed. All right, so that's my value there. So now I'm going to bring down the sum from I equals 1 to n. So now, what we can do is, remember, we want this in terms of I, and everything else I'm going to bring out to the front. So I'm going to bring the 8 over n cubed out to the front, and I'm going to leave the I term on the inside. Okay, so I squared. We have our limit as n approaches infinity. Okay, so now I know this. We have a formula for that, right? Our formula for the sum of I squared from 1 to n is going to be n times n plus 1 times 2n plus 1 all over 6, if you remember that, right? Okay, so that's what this equals. And then we'll bring down our 8 over n cubed in our limit, n approaches infinity. All right, so what will happen is when we distribute this, and let's kind of do this off to the side here so we don't have to rewrite everything over again. But when I distribute here, I'm going to get n squared plus n, and then we'll multiply that by 2n plus 1, right? So then we'll distribute here, so it'll be n squared times 2n, 2n cubed, and then 2n squared times 1 is n squared, and n squared times, I'm going to do n times 2n, sorry, it's going to be 2n squared, and then finally n times 1 is just n. Alright, so then I combine like terms, and what I'm going to get here on top is 2n cubed plus 3n squared plus n all over 6, right? Bring down all this other stuff. Okay, so now what I can see is that 6 and the 8 can reduce, right? So it'll be 4 over 3. And then also we have an n here that can, and I should have actually canceled this out from the start. I could have canceled out here this n with one of these. So I should have done that. But we'll do it here. So I'm going to cancel out one of these n's, so I'll make it where we have 2 n's left. And I'm going to cancel 1 from here, so I just have a 1 there. Cancel 1 n from there, so I just have 1 n left. Then you cancel one end from there, so I have two ends left, right? So this whole thing goes into a regular 1, but here the exponent turns to 1 and the exponent turns to 2. So we'll end up with, and I'm going to keep this 4 on the outside here, 4 times the quantity of 2n squared plus 3n plus 1 all over, and then I have n squared on the bottom, and 3, so 3 squared. And now we can distribute, right? We can distribute. Let's put this 3 underneath all of these at 3n squared. So it's going to be, all right. And so that'll be 4 times the quantity of 2n squared over 3n squared plus 3n over 3n squared plus 1 over 3n squared, right? And so when I simplify that, what's going to happen is these ends cancel out, right? This end, one of these ends cancels out with one of these ends, and this one, nothing cancels out. But when I take the limit as, well, let me rewrite it one more time. So the limit as n approaches infinity of 4 times, and I can actually bring the 4 out to the front, like in front of the limit if we wanted to, right? That's a limit property. But I have 2/3 plus these 3's cancel out, so forgot about that. So it's 1 over n plus 1 over 3n squared. Okay, and remember, whenever you have an n on the bottom or a variable on the bottom and it approaches infinity, and the constant's on top, that's going to go to 0, right? Because as n gets bigger and bigger and bigger, and you have 1 over that bigger and bigger and bigger number, it'll become a smaller and smaller fraction, closer and closer to 0. Same with this one, right? As n approaches infinity, that's going to go to 0. So really, all we have left is 2/3 times 4, and so it's going to be 8 over 3. That's going to be our final answer. All right, so that was a long problem. And so I don't know if you remember when we did the definition of the derivative problems, and those were kind of challenging. We had to that was the limit as h approaches 0 of f of x plus h minus f of x all over h, right? And we had to do all kinds of manipulating. So this is almost on another level, right, where we have limits and sums, right? We had to use our sum properties along the way, and then we used our limit properties and skills and concepts along the way. And so, yeah, these questions are definitely pretty challenging, okay? But, yeah, anyway, that's how it's done. And they're very similar. Once you see this one, like with the x squared, like all the x squared are pretty similar to this. Obviously the a and the b will change. That'll change things a little bit. But, yeah, they're all going to be pretty similar to this.